So in this video, we'll be talking about the equilibrium constant, or what we call Kc. C for constant. Equilibrium constant is basically a numerical value to when the exact to the amount to the equilibrium, how much of the of each of the reactants and the products are actually there. So if we have this equation A plus B give us C. Can you guys see this section here? Those, okay. Keep an eye on those. And then let's write down the Kc, or the equilibrium constant, equal to concentration. This parenthesis means concentration of products to the power of their coefficient, divided by the concentration of the reactants to the power of their coefficient. If we want to apply and figure out, write down the formula for the equilibrium constant for this reaction, we can say that Kc is equal to concentration of C, right, to the power of C small, divided by concentration of A to the power of A times concentration of B to the power of B. That's it. Very easy to apply. Okay, so we'll have lots of problems that we can figure out with this very easy formula. So here you can see this is the formula. So let's try to write the equilibrium constant for this equation. So can you pause the video and try to write it and then see the answer? So CO2 plus, so CO2 plus O2 and 2CO. Okay. Okay. Again, so we can write down that Kc for this equation is equal to products over reactant, the concentration of CO, it's 2 here, right? Let's write down 2, to the power of 2 divided by the concentration of the reactant to the power of their coefficient. 2 from here. O2 to the coefficient of 1. So this is how to write the Kc for any um, equation. Products over reactants. Here, products over reactants. Calculating the Kc. So if we have H2, that's another equation. So this is number 1, and this is number 2. Number 3, equation number 3, H2 plus F2, 2HF. If we want to write down, you can pause the video and try to write down your Kc, or the equilibrium constant, will equal to product to the power of the coefficient divided by reactant, the concentration of the reactant. And the coefficient for each one is 1. So here you can see it. And here, if I give you numbers here, you can just apply it and get the results. So this is what we're gonna do. Just applying the number, reading the problem and applying the numbers. For example, so this is an example before we start the study checks. So the concentration of each species in experiment number 1 are, so H2 is this much, the concentration 0.1 molar, and the I2 is 20 mole, and HI, the product, is 1.04, and the Kc is equal to products, which is this one, this number, to the power of its coefficient divided by the reactants, multiplication of the reactants. And this is always at a specific temperature for each reaction. So balancing an equation will come in handy now. It's so important. So here is a problem. Here it says, okay, so this is a decomposition of N2O4 to 2NO2. Okay. Okay. N2O4 decomposed into 2NO2. AC, and the numbers are, so 045 and 031. 045, 031 mole. So this is the concentration. So AC will equal to products. You have to write the equation to the power of the coefficient divided by concentration of reactant to the power of coefficient. Apply your numbers. So product, which is 031, divided by 045, Of course, don't forget to apply the 2 on the top. Do your calculations, and you will get 0.2. Oops, 0.21. So this is the equilibrium, the numerical value of the Kc at 100 degrees for this reaction. Okay. Another one. This is the example that we were discussing. So what is the Kc at this temperature if the concentration as follows? So you get the Hi, so 0.35 to the power of 2 because you have coefficient 2. Okay, so this is the equation and we will apply the number. So 0.35 to the power of 2 divided by 1.2 times 1.2. You will get 8.5 times 10 to the power of minus 2. And this is the equilibrium constant. How to use the equilibrium constant? So, for example, this is the SO2 plus O2 give you SO3. So initially, these are the concentration of the reactants, SO2 and O2. As you can see, they're very high. After a while, and specifically at equilibrium, you can see that the product is already done, and here those a quantity of the oxygen CO2 are basically lower. So you can see that the concentration with the reactants are higher than the concentration of of the product. So we call this will result in a large Kc. So the mixture is mostly product, which means you will get a small Kc. There are few cases here. If you have more products than reactants, then your Kc will be large. If you have more reactants than products, then your Kc will be small. So let's see this one here to see how it can be small. So to get a Kc small, then we will need to get a big Kc, then you have to have mostly product. So because the product is the one on the top, so you have to have mostly product and few reactant to get a big Kc. The opposite will happen when you're looking for a small Kc like this reaction. So here you can see that the product on the top are small comparing to the reactant. You can see the photo here. So you got a very small number of the Kc, minus 9, 2 times 10 to the power of minus 9. So we have at equilibrium, when reactants equal products, the Kc is always around the 1. If it's lower than 1, then it means that it's mostly reactants. If it's bigger than 1, then it means it's mostly products. If it's around 1, then the reaction is actually at equilibrium. Uh, So here are some examples. As you can see, the first one here, you have 2 times 10 to the power of 11, which is more than 1, which means it's mostly product. Here, 1.1 times 10 to the power of 7, also bigger than 1, then mostly product. 1.6 times 10 to the power of 2, also mostly product. Here 1.2 times 10 to the power of minus 1 less than 1, then mostly reactants, and the same thing minus 9 less than 1 says, so it's mostly reactant. How to use the equilibrium constant. To use the equilibrium constant, so here you go, it's the same thing. Find out for the reaction of carbon dioxide and hydrogen the equilibrium concentration, or this for the carbon dioxide, that for the hydrogen, and this for the water. What is the concentration of CO? So it give you the concentration of this, concentration of that, and concentration of that, and looking for the concentration